Thank you. First, I want to thank organizers. It's always a great pleasure to be in LA during winter, and also a great pleasure to visit, IPAM. So everything is great here. So I'm going to speak about certain property, which I will be calling shift invariance, which is valid for a variety of different systems of statistical mechanics. And what I will start by presenting just one instance of this property for one particular model so that you can have some idea what is it about, and then I will explain to which generality this can extend. So the model that I'm going to speak about, that's a model of directed percolation. So what is this? So you're looking at the square grid, and you're taking 2 points on your square grid, maybe A and B. Now you're looking at the paths which connect points A to B, and these are going to be monotone paths. So they're going up to the right, and that's what I'm not going to do. And so there is a collection of all possible paths. So that's one possible path, that's another possible path. There are finitely many of those. Now, in addition, what you're going to take, you're going to attach weights to the edges of your lattice. So to each horizontal edge and to each vertical edge, you're going to attach a weight. Now, these weights are going to be random, and they're going to be all independent. Okay, so you have a huge array of independent weights. Now, given all this data for your points A and B, you compute some certain distance between A and B. So how do you do it? So you're looking at all paths which link A to B, and you are adding the weights along the edges that you encounter when you follow these paths. So that will give you a weight for a path. But now for the points, what you are trying to do, you're trying to minimize this sum. So the minimum sum, that's what we call D of A and B. And that is, that's percolation model. So for each 2 points, you get some kind of a random distance between these 2 points given by D of A and B. Okay, so we are going to proceed with some particular choice of the weights for this lattice. So I'm not going to speak about general weights, but I will instead concentrate on the weights which are going to be white noises. So what does it mean? So in order to create these white noises, what we'll start from Brownian motions. So we'll take a collection of independent Brownian motions. And now for 2 points, maybe on this picture there's a point 0, 0, and then there's point T and 0, 1, 2, 3, 4. For 2 points, what you're trying to do, you will be minimizing over paths. Now these paths are going to look a little bit differently, but essentially the same. So you will follow horizontal for some time. Then you will jump to the second horizontal. You will follow it for some time, for the third horizontal, for the fourth horizontal, etc., until you reach your finite point. And what you are going to do, you are going to look at the increments of independent Brownian motions over these horizontals. So you have a first Brownian motion here, so you took its increment over this segment. Then second Brownian motion here, you take its increment here. Third Brownian motion, fourth Brownian motion. Now there is still optimization problem here. Namely, you are optimizing over the choices of the points where you're making jumps. So there's a simplex of all possible of these points, and you're looking at the minimum over all possible choices. And that becomes a certain random variable, right? For if you take 2 points, SMTN, you minimize over all paths, that's a random variable. Is it clear? Are there questions?
If these are independent, why don't they intersect?
I just wanted to show that they belong to different lines. That's it. No, they're completely independent. Yeah, they're independent here. So
the distance may be negative also.
Yeah. In this situation, the distance may be negative. That's correct. So this is sometimes called Brownian directed percolation, and often people, instead of looking into minimum, they look into maximum, and then it's called Brownian last passage percolation. But for Brownian motion, it doesn't matter, because multiplying by -1 interchanges minimum and maximum. So you can choose whatever you prefer more. For the distance interpretation, maybe minimum is a bit better. So what is known about this Brownian directed percolation? Well, if you fix one of the points, maybe the starting point to be 0, 0, and then start to vary the ending point, and you look at the joint distributions of your distances as you vary end points, then it turns out that essentially everything is known. Namely, there are certain Fredholm determinant expressions which you can write down, and then you can analyze this Fredholm determinant, and you can answer any asymptotic questions you like. So there is an explicit formula, then it's just a question of working with this with explicit formula, and people somehow know these days how to work with this kind of formula. So in this way, it's perfectly known, and the reason why it's known, well, one of the first reasons why it became known is that Robinson-Shenset-Knuth correspondence, which was already mentioned here in the morning, allows you to reduce the question about percolation, about Brownian percolation, to the question about so-called Dyson-Brownian motions, so about evolution of eigenvalues of a matrix whose matrix elements do Brownian motions. And then that is very well studied object in random matrix theory, and then you can reduce your study to study of that known object, and this allows you to get all kinds of asymptotic results. So that's if you fix one of the points. Now, up to very recently, for the situation when you don't fix one of the points, but instead you're looking at a joint distribution when both one endpoint and another endpoint is allowed to move, no precise formulas were known. So though there are still results which, RSK still gives you something, but unfortunately in this situation on the random matrix side, you also get something which you don't know how to compute, and therefore, RSK is not really helping you. Although, no formulas exist, it doesn't mean that you can't do anything. There are many articles where people proceed without formulas. I don't want to touch that, but, this is good to have this in mind. So in particular, the simplest question that you can ask, which would, yeah, that's.
Do all the Brownian motions start at 0? Is that why it's harder? I mean, all the Brownian motions start at time t.
So these are independent Brownian motions. Since you're only looking at their increments, it's not of particular importance where they start.
And then why does it matter whether you start at 0, 0 or?
Well, what matters is that there is a joint distribution in which you fix one endpoint and you vary another one. So maybe you're asking about joint distribution as from distance from 0, 0 to 0.12 to 0.21 to 0.10, etc. But in this joint distribution, one of the endpoints is the same. Yeah. It's not like on the very next picture when you have now 2 points and you have one pair of points and you have another pair of points. So that's a different situation because now that's a more complicated joint distribution. So that's the simplest question that you can ask. What is the joint distribution of these distances, these random distances, when all the points are different? So something like that picture. Well, it turns out that now here is our first theorem, which we got with Alexei Borodin from Boston and Michael Wheeler from Melbourne. That turns out that you actually can compute this distribution. And the reason why you can compute this distribution is the following property of the shift invariance, which holds for this Brownian directed percolation. Namely, imagine that you are taking your points C and D in this picture, like this C and D, and now you take both of them, and now you shift both of them to the left by some distance. So the statement is that the joint law will remain the same when you do this shift. So let me try to explain what that means. So certainly one-dimensional distributions are unchanged. This is just invariance of the white noise. So of course, if you shift everything by translation invariance, the distribution is the same. But if you're looking at the joint distribution of two things, then at first it looks that configuration becomes very different, right? So now it were these 2 points, now these are different combination. There is different pair of points. However, the theorem is that the joint law is actually exactly the same. So in particular, what you can do, you can shift it to the extreme position, like here, you're looking at A, B, C, D, and then you shift your point C so that it coincides with point A. And now you reduce to the situation in which, as I told you, we have access to the joint distributions because they are given by Fredholm determinant. So in this way, this shift invariance reduces unknown distribution to something known. So in this shift invariance, I want to emphasize that what was important is that this configuration of points was not completely arbitrary. Namely, if you want this green segment was necessarily intersected with this blue segment. And this is really a necessary condition, because if you think about taking these 2 points C and D and moving them very, very far away to the right, and as soon as they are far enough, the noises which enter into the definition, they're completely independent, right? Because these from A to B will depend on this noise, and from C to D, if C and D are here, depends on different noise. And therefore, in the extreme situation, it's independent, while in the original situation, it's very dependent. So there is no hope that the shift invariance valid in general. There should be some restrictions to that. And what we show is that the restrictions which appear is that D should be to the left and up from B, and while C in this situation, this is to the right from A on this line. So we don't know elementary proof of that. So all the proofs, they use some quite advanced machinery in order to be done. So there is not a simple bijection that you just reshuffle maybe this part of the picture here. That we don't know.
So D can't be less than B, and D has to be bigger than B, is that what you said?
So what, right, so D should be like in this and that direction from B. So it should be to the left and up from B. So if you want, then if you take any monotone path from C to D and any monotone path from A to B, then they should necessarily intersect. That's the condition, that every monotone path should intersect. So similar property holds for multi-point distribution. It's not only about moving one pair of points, and I will get to that very soon. And moreover, it turns out that that's not just a property of this Brownian model. Instead, that's a property which holds in a wide generality. There is some symmetry. And now I'm going to explain to you to what kind of other models we still have similar property. There is a chart of models which appeared in our text for which we can prove something. So there are many models here, and there is no hope that I will cover all of them in this talk. So one object was already mentioned but not defined properly, maybe defined but very briefly. That is color stochastic six-vertex model, and I will go to this definition later today. And there are various particle systems which you can work with. There is this ASAP, which was already mentioned. There are various directed polymers, last passage percolation models. There are various things here. So if you are particularly interested in learning how the shift invariance looks at one instance, then let me know. Otherwise, I will just cover some of the instances of the models on this chart. But our theorem is that actually there is a statement about shift invariance of something for each of these models. And that's what I'm trying to explain. Okay, so let's start with another example. So here, there is a realm where maybe these statements of great interest in these realms of directed polymers. And now I'm going to give you an example of this statement for the directed polymer. So I will need to define to you what is a directed polymer. So we'll look at the so-called gamma polymer. So gamma polymer, that's again, something is happening on the lattice, similar to our last passage percolation model. But now the lattice is a little bit strange one. So it turns out that what turns out to be nice is that to do the following thing. So you're looking at Z squared, but now the edges are either diagonal, like here, or horizontal, like there. Again, we are going to put independent weights on the edges. Now, on each horizontal edge, we are going to put independent gamma distribution with some parameter kappa. Here is the formula for the density of gamma distribution. And, well, kappa is a fixed number, which is fixed once and forever. So it's the same for all the lattice points. But in general, these gamma distributions are all independent. Now, for the diagonal thing, our weight is going to be 1. So no weights on the diagonals if you want. And now we are doing like finite temperature analog of the directed percolation if you want. So it's very closely related to what Ivan was speaking about during the first talk. So now for 2 points, x, y, and x prime, y prime, we again are doing something over all paths, but now we are summing over all lattice paths product of the weights which you encounter as you move along the path. So in particular, you don't take any weight for this diagonal thing, but you take these gamma functions as you move horizontally. And it is called partition function of gamma polymer. So you should think about your polymer as this random string from one point to another, and it is partition function because you sum over all configurations. So there is something good about these polymers. There is a very large degree of integrability. You can compute many things about this polymer. That was noticed first by Timo Seppäläinen, and then by Ivan, Tima, and Hao, and then there was also another paper by Neil O'Connell and Janusz Ortman. So people know that this is quite a good model. Now let me give you the statement of the shift invariance for this model. Suppose that you take some path So you take one pair of points, maybe this one and this one, and you will be doing the same thing as before. You will be shifting this pair of points to the right by some finite amount. So like this black path turns into this black dashed path. And the statement is that the law will be invariant under this shift when you look at this law jointly with several other polymer partitions functions which are not going to be moving at all. Namely, what you can do, you can go from this blue area here to this blue area here. So look at any polymers which start here and here. And you can go from this orange area here into this orange area here. So look at any polymers which start here and start here. So all the orange and blue things, they're all fixed, and the black thing is being moved. And the statement is that the law is not going to change. Question?
Yeah, maybe I'll wait.
Okay. So that's our shift invariance for the gamma polymer. Now, gamma polymer might be too complicated because there are these weird gamma weights there. So you can simplify it. Well, okay.
Question. No, something special about the gamma weights that makes this work.
Right.
Is it Yang-Baxter equation at the bottom?
Well, it is related. So on the very top, our statement for the six-vertex model is related to Yang-Baxter. Our proof relates to Yang-Baxter relation. So you can say that yes, there is some relation to Yang-Baxter equation because of that. And okay, I will get to the point. So there is this property is not a property which holds for any weights. So we know counterexample. We can come up with weights for which it will fail. So it's only for the integrable weights. We don't know all of them, but for those which are integrable, that's where we have this property. Okay, so let's simplify our gamma weights. So the way to simplify them is to use some kind of a central limit theorem. Namely, if you think about huge domain, then your independent noises, which were gamma distributed, the asymptotical will become just Gaussian weights. So there is some scaling regime in which your field of independent gamma weights will converge to just a white noise. So just for two-dimensional Gaussian field with delta correlations. In this regime, your gamma polymer, it will converge to another polymer, which is sometimes called continuum Brownian polymer. So essentially it does the same. It takes 2 points, and now you sum in over all paths, but now these paths look like Brownian bridges, and what you're collecting is a white noise. Now, analytically, it's not an easy object to make sense of, because what you need to exponentiate a white noise, and it's not so clear how do you really exponentiate two-dimensional white noise. So one way to get your hands on this object is to instead think about the stochastic partial differential equations which it satisfies. So the way to see this equation is as follows. If you just look at your polymer partition function, then it satisfies an easy recursion. Namely, if you look at the value of your partition function here, then you can make your first step. So the first step from this direction is either horizontal or it is diagonal. And therefore, there is a relation that the value of partition function here is equal to the linear combination of partition function here and partition function here, where the coefficients, well, one of them will be equal to 1, another one will be equal to your gamma distribution. And you can try to take a limit of this recurrence relation, and you will get some stochastic partial differential equation which is satisfied by the limiting object. And here is this stochastic partial differential equation. So it is sometimes called stochastic heat equation with multiplicative noise. Multiplicative because you see that there's a white noise eta here which is being multiplied by your solution. Now if you formally take a logarithm of this z, which appears as a solution of this equation, then you will get something which Igor wasn't happy about. You get in KPZ equation, these 3 letters, but I can decode them to you. So there's Kardar-Parisi-Zhang equation. You don't need to know.
That was the SPD.
Yeah, and by the way, SPD is stochastic partial differential equation, right? So what is this equation? You don't need to know too much about it. So all you need, for this talk, all you need to know is that it is some deformation of heat equation in which you add, nonlinearity, and which you also add white noise. And how does it appear? So it first appeared in 1986 in the article by Kardar-Parisi-Zhang. So what they were interested in the growth models of one-dimensional interface. And then what they figured out is that under some somewhat natural assumptions, all these growth models, they should approximately look like solutions to this equation. And they suggested that, okay, this equation is a very good model if you want to think about the growth of something. So this is an evolution model. Since 1986, there were numerous models of various growth which were shown to converge to this KPZ. So you start with some very different model, but then you do certain scale and limit transition, and you arrive at this KPZ. So if you want, their prediction was confirmed that indeed this object is very good representative of the class of models, because many other things can be linked directly to it. So what is it about this KPZ equation? What is the new thing that we can prove for it? What is the shift invariance for it? So you're looking at the solution of this KPZ equation or of this stochastic heat equation. Now you're going to have several solutions. These solutions will be different in the sense that they will be starting from different initial condition, but they will be related in the sense that the white noise which participates will be the same. So you couple the solutions through the white noises which appear into them. The initial condition that you are looking for is a delta function initial condition for the stochastic heat equation. For the KPZ, it's usually called narrow wedge initial condition. Now, so it's not clear how do you take logarithm of delta function, but you can think formally about that. So now what you are doing, you're looking at the solutions of this equation of two solutions, in one of which you shifted your starting point. So you shifted your initial condition from delta function at point y to the delta function at point y plus delta. And now you're computing the value of the solution to your equation, either at point x or at point x plus delta, and that is happening after some time t. And the statement is that not only the law, one-dimensional law is invariant, but actually it remains invariant if you simultaneously throw into the picture several other solutions. So you can also start your solution from any point to the right and look at the value at the point on the left, and you can look at your solution which starts at any point on the left and look at the value at the point on the right. And then again the statement is that when you make the shift, then the joint distribution is invariant under this shift. That's a statement of this shift invariance for the KPZ equation. Now, in this origin, in this domain of Kardar-Parisi-Zhang equation, various related models, there is one universal object, which is called sometimes Airy sheet, and sometimes it's called directed landscape, depending on the community to which you belong. So essentially, there are various ways to define it. One way to define it is that there is a large time scaling limit for the KPZ equation, what's happening with your surface growth if you wait for a very long time. That's one definition. Another definition, if you're more like a person from the who likes directed percolation, then you should think about some percolation with some weights, and you're thinking about computing the distances between some 2 points which are very, very far away, and you're trying to say, okay, what is the scaling limit of this object? And then there are general conjectures which say that the large time limit of KPZ and the limit of directed percolation for arbitrary ways, it should be given by the same object, which is some function of 4 variables called space-time Airy sheet or directed landscape. We don't need all these 4 variables. We'll just take only 2. So you are thinking about some random distances between 2 lines. So you will have points here and points here, and you will be computing the distances between those. And you will be looking at the scale and limit of these distances, and that's a limiting object there. So it's called Airy sheet. So conjecturally, this should appear for the last passage percolation with almost arbitrary weights, and also for KPZ. It's not rigorously known at this point, but what is rigorously known is that for Brownian last passage percolation, there is a theorem from 2 years ago that indeed it converges to this object, and at least this shows that this object is not something pathological, that it exists in a sense. And there are various other numerous results where you don't know how to prove the convergence to the entire object, but maybe to some marginals of it. For example, for the KPZ equation itself, there is a 1-point result, which says that if you just look at the just one-dimensional random variable, which is the law of solution of KPZ equation may be at 0 at time t, then as this time t becomes large, if you do proper scaling, then you converge to the value of this Airy sheet at 0.00, which is the same random variable as the Tracy-Widom distribution. Okay, so there is this object, universal object in this area. And for this object, again, we have a statement of shift invariance. And the statement is very similar again. So you're again looking at this distance between 2 points x and y. And the statement is that when you shift these 2 points together by some delta, then the law remains the same. And the statement remains the same if you look at it jointly with any other distances, as long as you again have an intersection condition. So you might look at distance from point on the right to the point to the left, or from the point on the left, point on the right. So that is our shift invariance.
You're making it more and more fancy example. What if you make less fancy? Like, let's take simple random walk. Is there
I will reach to that. So at the very end of the talk, you will see the statement for a simple random walk. Exactly. Good. That's a very good question. Okay, so for now, let's look for the fancy example. So you can ask, how general is this shift invariance? So what I showed you is that there are some specific integrable weights for which last passage percolations and directed polymers, satisfy this shift invariance. And there are some universal objects like, KPZ equation or Airy sheet, which also satisfy this shift invariance. Now, the question that you might be asking, okay, for what other ways is it true, and for what other ways it fails? So unfortunately, at this point, we don't know. All we know is that there are examples where it holds, and there are examples when it does not hold. That's what we know. So, okay, if we don't know anything, what do you need from ways to do this, and how do we even, approach the question?
Yeah. I must understand that the Airy sheet and the KPZ stuff hold from the gamma polymer thing, or not?
Well, from gamma polymer, you can get KPZ equation as a scalar limit. Now, the limit from KPZ equation to Airy sheet, it is a conjecture, so it's not known. But what is known is that from this object, you can converge to Airy sheet. And that's how we actually proceed. So, the truth is that, we start by proving only one statement, of course. We don't prove, 20 different statements. So what we start from, we prove a shift invariance statement for the color stochastic six-vertex model, which we will define in a second. And then the rest is obtained through various procedures which link all this chart of models together. So, these procedures are different. Sometimes you just do direct limit transition, but sometimes you need something more complicated. For example, here you need a procedure known as fusion. Some of these points rely on some analytic continuation statements. So there are different procedures, but in a sense, you would think that they are simpler. All these limiting procedures are simpler than the master statement, which we are proving on the very top level of this color stochastic six-vertex model. So let me define you what is this color stochastic six-vertex model. So first of all, what is a six-vertex model? Well, six-vertex model, that is just configuration of lines on the square grid. So like here, you just have lines. So your lines are allowed to share vertices, but the lines are not allowed to share edges. So they can touch to each other, but it's impossible for the two lines to share the same edge. Now, about this thing, you should think as if it is a white and black model. Although I just told you that this is just a collection of lines, but instead you can think that it is a coloring of the entire grid into two colors. So some of the lines are black, and some of the lines, well, which you can treat as an absence of lines, they are white. So that's your black and white model, six-vertex model. It's called six-vertex just because locally near each vertex there are 6 possibilities how your local configuration looks like. So now you add colors to here. So the only thing that you change now, say that instead of black and white, now you allow arbitrary color. So that's the picture that you get here. So now that's a configuration of lines on the grid, and the lines are allowed to have different colors. Now I should warn you that sometimes the representation that is used for the six-vertex model is the one in which the lines are not allowed to intersect each other. When you speak about the colors, then you need to allow intersection. So this blue thing intersects this black thing. Okay, it's also called stochastic. So what does it mean, stochastic? Well, stochasticity means that we are dealing with a model with specific weights, and these weights lead to certain procedure which we can use in order to sample our configurations. So if you want, there is just a stochastic recurrence which gives you a configuration slowly. So for this procedure, we need specific boundary conditions. So these are so-called domain wall boundary conditions. So what this means is that in the bottom of the picture, you have color 0, or you can think you have nothing there. And in the left, here, you have growing colors. So there's color 1, color 2, color 3, color 4, color 5, etc. So the paths enter here, colors are growing. Now in this picture, you will start sampling your configuration sequentially from this corner and going into that direction. Suppose that first you can want to sample the corner. So you sample the corner and you see, okay, what are the possible choices here? So in principle, there are only two choices, because either the red can proceed horizontally or red can turn up. Now we choose a specific weights, and all the weights are shown here. These are the weights attached to our 6 types of vertices, where in this picture, this gray is smaller color and black is larger color. Now, the way the weights are chosen is so that whenever we need to make a choice, like here, the weights actually sum up to 1. So here you have B1 and 1 minus B1. So what it means is that we can flip a biased coin with probability of heads being B1, and then as a result of this flip, you choose whether it will be horizontal or if it will turn. So that's how you make a choice here. Now you proceed to the next point, like here. Again, there is a choice between two opportunities, and you flip in a coin, independent coin, to do that. Then the next position, okay, next position is similar so far. Here something new happens. So now the smaller color is entering from the left, and larger color is entering from the bottom. But that's again a choice which comes according to other weights with probabilities B2, 1 minus B2. So you can again flip a coin to make this selection. Here it's very easy. You know, there's just both colors are gray, so you don't have anything to choose from. And that corresponds to the fact that in our weights there's a weight 1. So you're just making a unique choice. So you propagate these dynamics and you sampled your configuration in the entire quadrant. So now you get a random configuration in the quadrant. So you might look at large simulations. So thanks a lot to Leo for making this simulation. So that's a huge picture, and you can see that something interesting is actually happening here. So there are these lines formed by different colors, and I believe that it's not fully understood at this point why these lines and how to describe the fluctuations on these lines. So we know something about this picture, but we are very far from knowing everything about this picture. But that's a interesting picture worth studying.
Second-class particles.
Yeah, the colors are like second-class particles, exactly.
So you can make some conjectures, or Alexa can make some conjectures.
About something, but I think that probably about the scaling limit of this curve, I don't know if anybody can make any conjectures. I mean, if you look here, it seems like there are some red curves here, right? No, you don't see those? but it's not exactly a straight line, right? It's fluctuating a little bit around. And you can ask about this process, how it fluctuates. What do you mean? That's not a straight line. It has a slope, but it has fluctuations around this slope. So if you ask about fluctuations. Right. So in the first order, it has a slope, but then you can ask about fluctuations around this slope, and that's yeah.
It's time fluctuations.
What?
It's like time fluctuations in like the interior class with
Percolation. Probably. Yes, Scott?
It's a theorem that it's asymptotically a straight line through scale.
That I think is no, it's not.
For K-sep it is.
For K-sep.
But for A-sep, for 5 vertex, it's a theorem.
It doesn't even look true. Look at the two red.
No. I think that it's almost. There is a theorem. We know the density on this picture. We know the density of colors on this picture. So in principle, you can relate it to saying that it's essentially a straight line. This thing.
You can say
Oh, given particle you don't know, right. Given particle you don't know that it's a straight line, but you kind of know that, if you just look at the distribution of colors, and it looks somewhat like that the colors vary, how you see them on this picture. No? Okay, let's go on. Anyway, that's not the topic of my talk for today. So, there are lots of history about the six-vertex model, and there is no way for me to cover all of it. So it appears almost like 85 years ago. And what is relevant for us is that first it appeared as just without any colors. The idea that you can add colors to it is fresher. It's appeared like 50 years after the original introduction of the model, and that was when people realized that there is related to some representation theory, and then the representation theory, it was clear that you can actually add more things, and now it became clear how exactly you add these things. Now the stochastic versions, they appeared first in 1992 in the work of Guai and Spon, and then slowly all things got recombined, and now we can actually prove something about these models. Okay, now what is the shift invariance for this particular model? In order to speak about the shift invariance, what you need to define so-called height function. So height function is just a way to think about the model. Instead of thinking about configurations, you will be thinking about certain integer valued functions. So these functions will be parameterized by colors, and the height function h larger or equal than y will be, for a given point x and y, will be counting the number of paths of colors greater than or equal than I, which pass to the right or below from a given point x, y. For example, here I show as an example the height function with parameter 2. So it's h2, so it counts the paths of colors 1 and 2. So here there are no, it's counts paths of colors 2 and greater, so 2, 3, 4, 5, etc. So everywhere here until you reach something it's 0. Now you cross the first path, now it's equal to 1, now it's equal to 2, 3, 4, 5, etc. In this way you can just parameterize your configuration by the values of all possible height functions. If you know all of them, then you can reconstruct configuration. So in terms of these height functions, we prove the following statement. So what we prove, again, some kind of shift invariance, only now slightly different things is being shifted. So in the polymer world, what we were shifting was one endpoint and another endpoint. Now you shift your observation point. So this is your u, and I'm shifting it in vertical direction here. And simultaneously, what I'm doing, I'm shifting the color which you are looking at. So you're looking at the simultaneous shift of color and of the observation point. Well, of course, color is somehow related to the vertical coordinate just because of the nature of our boundary condition. Because our boundary condition was this growing color. So you can think that it is essentially the same thing, only restated in a slightly different language. And the statement is again of the same nature. So again, under the shifts, the distribution is invariant, even if you take it jointly with several colors which are not being shifted. So that's a theorem for the six-vertex model. So let me just give you some elements of the proof. So how do we actually prove this statement? So it turns out that in order to prove this statement, what we need to do, we need to introduce some inhomogeneities here. So we pass to even more complicated statement, just contrary to what I was asked about. And now the model will be not homogeneous, so the stochastic rules will start varying by rows and columns. There will be two sets of parameters, u's and v's, which you work with in order to introduce these inhomogeneities. And your weights b1 and b2 will now depend on these parameters u and v in the following way. And of course, this way is chosen so that they satisfy Young-Baxter relation. So that's how it appears. Now, what's the advantage of this inhomogeneity? Well, the advantage is that after you multiply everything by denominators, now you can treat your identity between distributions as certain polynomial identity. So now you have some polynomial identity in variables u's and v's, and you are trying to prove this polynomial identity. Now you can count the degree of polynomials which are involved here, and afterwards you can say that, okay, so we have polynomial identity, so it's enough to check it that it's valid in enough points, and then it's valid for all points. Now there are special points where simplification is happening. So from looking at these ways, you can notice that when u's are equal to v's, then the weights, some of the weights vanish. And that's very nice. So you can use this vanishing, and then you can combine it with application of Young-Baxter relation in order to make an induction step. And then you reduce the statement from the domain of some size to a statement of domain of slightly smaller size. And this eventually allows you to proceed and prove the statement. So that's a sketch of the proof. Now, we've been discussing this result for some time already. I was given talks about this in October, and we showed the proof to some other people. And we have many smart and quick people in this area, so you're not surprised that people came up with some different ideas how they can be proven that. So I think that neither of these two other approaches has been posted, but there are now two other approaches. So Duncan Davern came up with some very interesting proof which is based on some symmetries of Robinson-Shenstedt-Knut correspondence. So after he uses Robinson-Shenstedt-Knut correspondence, he noticed that there is some symmetry in the end which is somewhat similar to the symmetry of symmetric functions with respect to interchange of the variables, but you need to carefully look into the exact details to figure out how that works. Anyway, from that, he managed to produce another proof for the last passage percolation case, for the zero temperature situation. Now, Pavel Galashin had some argument which uses Hecke algebras. Among the lines, like Losha Bufetov earlier today was also speaking about Hecke algebras and how they're related to the vertex models. So again, similar game with Hecke algebras, and also Pavel used very nice idea that shift actually can be obtained if you do two reflections, which is kind of natural, but proper realization of that in the end will give you another proof of this theorem. Now, what's important?
Vertex colored or not? The last one.
For colored, yeah, colored. So what's important is that still both these proofs, they use lots of integrability. So of course, Robinson-Shenstedt-Knut correspondence is something very integrable. It won't work with arbitrary weights. You need some very nice weights. And of course, Hecke algebras also won't work, for arbitrary thing. You need some very precise things so that you have the relations given your Hecke algebras. So you might be wondering, either something simpler or more conceptual, either some explanation. Can you get these kind of statements in the simplest possible instance so that you can at least get some feeling what is it all about? Well, unfortunately, in general, we don't know any simple proofs for this statement. However, you look at the huge chart of the models here, and there are some of the models which are extremely simple. Namely, in this chart, some of the models are just Gaussian. What is good about Gaussian random variables? Well, what's good is that when you need to check some identity, it's enough to check that covariances coincide. So Gaussian vectors are uniquely fixed by their covariances. So instead of checking that two distributions coincide, you will be just checking that the covariance of the vectors appearing in these distributions coincide. And that is something that turns out you can do, and then it will give you some idea of why this distributional identity is happening. So now let's reduce to the simplest possible case of the Gaussian models. So the simplest possible Gaussian model in the class of the models where the shift invariance still happens is the following version of stochastic heat equation. So you're looking at the evolution equation for the h. So its time derivative is equal to the twice space derivative plus white noise, and white noise is being multiplied by an explicit function, and this function is just a Gaussian kernel, like here. So you might be wondering, what's the origin of this thing? How did it appear? So there are two ways to arrive on it. One way is to start from the KPZ equation, and instead of looking at the large time limit, you can look into the small time limit of KPZ equation. That turns out to be the Gaussian object, so there's a simplification in the small time. Another way to do these things is to look at some of the colored models and then try to do hydrodynamic limit of these colored models, and then look not at the first term of this hydrodynamic limit, so not the law of large numbers, but the Gaussian fluctuations around this hydrodynamic limit. And this will give rise to the Gaussian equations similar to these ones. So for this equation, there is still the very same shift invariance. So again, you shift. You're looking at the solution, so there is a parameter now which is y, that is centering of this Gaussian kernel, and you can simultaneously be shifting y under the observation point where you're looking at your solution. And the statement again is going to be that the law is invariant under this shift, even if you're looking jointly with some other collection of points. Now, why is it simpler? Well, that's because the solution to this equation is just a Gaussian random variable, because that's a linear equation. You can just solve it using the fundamental solution of the heat equation. So that's a formula that you get. So the fundamental solution of the heat equation, luckily that's again Gaussian kernel. So you're getting that the solution is just double integral of white noise involving two kernels, two Gaussian kernels. Well, therefore, now if you want to check that some distributions are invariant under shifts, you need to check that covariances are invariant under shifts. So you need to compute covariance. You need to take two objects of this kind, multiply those, compute expectation. Not too hard, because you have white noises, and with white noises it's easy to compute expectation of the product. So in the end you get in some expression, which I am hiding in a small font here. What's important is that there are now it's a product of four Gaussian densities somehow, combined with various arguments. And then it's being integrated. Now you can stare for some times, like we did, a year ago, at this formula, and then you can recognize that, okay, actually, this integral of the product of four things has very nice stochastic interpretation. And here's the stochastic interpretation here. So this product of four things, that's an expected intersection local time for two Brownian bridges. So what does it mean? So you take one Brownian bridge which travels in time t from the point y to the point x, and another Brownian bridge which travels in time t from the point y prime to the point x prime. And now you want to count how much time do they spend together. Well, of course, formula this time is 0, so you need to have some proper normalization. That's this normalization is known in the literature under the name of local time. But after you do this proper normalization, essentially that's the time which they spend together. And you want to compute expected time. So how this product of four densities appear? Well, you're kind of thinking about what's the probability that they intersect here. And this probability is given by, okay, you need to travel from here to here, from here to here, and also from here to here, and here to here. And that's how you get in four Gaussian kernels. Okay, so your shift invariance is now related to the shift invariance of the expected local time of intersection of two Brownian bridges. Now, even that might be still too complicated, but now you're thinking, okay, why do we need actually two Brownian bridges? We can instead pass to the difference of these two Brownian bridges. And difference of Brownian bridges, that's a Brownian bridge again. So now we arrive at a statement for the just single Brownian bridge. And here is the statement. So you're having a Brownian bridge which travels from point A to point B in time t. Well, you can choose t equals to 1 if you want. And then you're computing the local time of this Brownian bridge at some level, c. And you're looking at the expected local time there. So expected amount of time that this Brownian bridge spends on the level c as it travels from A to B. And then our shift invariance in this particular case just says that this local time is actually invariant under the shift of the point c as long as c is between A and B. And well, if you dig in the literature, then you figure out that not only that is known, actually there is a formula for the law of this local time. So it's kind of well-studied problem in probability, and the law of the local time at point C, it's known. So here is the density. So the density is given by this formula right here. And well, what can you notice in this formula? So you see there are the absolute values of C minus A and C minus B, and their sum. So if C is between A and B, then the absolute value of C minus A plus absolute value of C minus B, well, that's precisely the length of the segment. That's B minus A. And so it does not depend on the value of C. So of course, if C becomes very large, then it starts depending. But that's, of course, expected because this local time should go to 0 as C becomes up farther up. So this is a necessary condition.
So the law, not only the expectation, is there.
Right. In this situation, it's not only expectation, but actually the law. But it's similar that, okay, let me first show it on the next slide. So similarly, in our discrete settings, you can again ask not about the invariance of laws, but invariance of covariances. Already, for example, for the stochastic six-vertex model, you're not asking about maybe you're not asking about the invariance of the whole height functions, but invariance of the covariance of height function. And then we can design a proof which will be linked to the discrete version of this statement. So there will be some discrete random walks, and again they will be intersecting, and there will be some invariance of intersection local times of the discrete random walks under shifts. And that will be related directly to the shift invariance of the covariance in the color stochastic six-vertex model. But of course, color stochastic six-vertex model, that's not a Gaussian model. So the covariance, doesn't tell you anything. So we still need to have more complicated proof of this, inductive nature, or this other proof that Pasha has to eventually, get the full result. Okay, so let me summarize. So what do we see here? So there is a class of models for which the joint laws are invariant under partial shifts of some of the variables in our observables. So you shift some of the points, and by some reason the law is invariant. So for us it's important because it gives access to certain distributions which were never accessible before, because we can reduce the cases with complicated geometry to the cases with simple geometry, where we actually know how to compute things. Now the proof, if you want the proof for covariances, then we can link it to the invariance of the local time of Brownian bridge with respect to shifts. But if you want the full proof for the law, then you need to follow more complicated path of introducing inhomogeneities and then proving polynomial equation by checking it enough points using Young-Baxter relation. And finally, we have, this still belongs to integrable probability. So what's very important for us is that this chart of models, of course, this chart of models was created by efforts of very many people who figured various connections between these models on these charts, how to get one of them out of another. But eventually, we know that this chart exists. And because of that, just from this color stochastic six-vertex model, we can get a whole zoo of different statements for different models here. And that's it. Thank you.